Okay guys, so let's move on to the next question. Before that I want to say that the reason we play Johnny B. Good is because Johnny B. Good was composed, this is not working, Johnny B. Good was composed in 1955 and this is around the same time that the pickup was invented, which is the parallel idea to a microphone. You see here's a microphone, so it's look like, and you have this diaphragm which is made of capacitors. So the inductance idea of how to collect the data, the sound that the guitar made, and amplify it based here on pickup, here on mics, and how to play bass guitar, electric guitar, which usually have this configuration. Okay, so let's move to the first question. The first question is going to be a really basic RL question, and I think it's important to talk about the basics of RL, because RL can get really complicated, and if you don't understand the basics, you are lost. So let's draw a simple RL. So RL circuit is actually, as the name implies, we have a resistance, so we have some inductance, which defined by L. And I want you to notice that I drew the battery with some space. It's going to be relevant in a few minutes. So here I have some inductance, which inductor is just, you can see here, it's just the line of the circuit, but I just do a helix motion when I draw it, and that's exactly what's happened usually when you have an inductance and a resistors, like a sawtooth, right, sign. So these have the value R and these have the value L. And the first question I want to ask you is why inductor actually make this circuit sensitive to the magnetic flux. Okay, so why inductors L makes the circuit sensitive to the magnetic flux, which is phi. Okay, so if it was not there, we can neglect the phenomena of magnetic flux. So let's talk about that. So first of all, what is the magnetic flux? Let's remember, so magnetic flux is actually the integral around some area A, okay, of B dot dA. Right, this is the idea. So what's going on when you have some circuit, okay, this is the circuit, I have some area that this loop, this current loop actually is closing. You see this area? This is A. This is A. So few things happen when I put an inductor. Okay, let's look at this area of a circuit, okay? So if I have this area, and instead of putting a line, I'm gonna put an inductor. A really simple one with just one loop. See, around one coil. Here it is, okay, just one. So if I'm gonna put it here, do you notice that the area is right now changing? Think about it. I have this area, okay, and if I put an inductor here, I have this loop, and this loop is actually popping out outside of the board. You see it? So actually I have also, here, I have also the area over here. Okay, so actually the effective area, the area is increasing when you put loops. Okay, how you can think about that? Easy way for me to do it. I imagine that I have a water with the soap. Okay, and when I take my loop, my electrical loop, and put it inside the water, I expect to see a bubble. Okay, and what is the size of the bubble? So the size of the bubble, if I have loop, is actually increasing because I have also bubble here in this part, in the circle that pop out of it. So I increase, and I want you to think about that I don't have one loop, okay? I have many loops. Look at this configuration, okay? I have many loops, and when I put it here, actually I'm increasing A. And remember that the example I gave you with the pickup? So pickup is about 8 thousandths, okay, 8 thousandths, 5 thousandths loops, okay? So it's really a lot of area that being added to the old area with no inductor. Okay, so inductors actually, so let's write A is increasing. The area of the loop increasing. Okay, increasing. Okay, this is one reason. The second reason is think about it, that if I'm taking my right hand rule, right? So this is the electric current that's going in this circuit. So if I try to see what is the magnetic field that go inside the loop, so look, I have here, right, it's going inside the board and outside the board, inside the board, outside the board. But you see that there's no really combination of a lot of arrows that join by, okay, that contribute together. But if you look at the spring, let's look at this example. So if I look at the spring, what's happening if I do the right hand rule? So if I do the right hand rule, I'm going with, let's go here like this. I'm going here with the inductors, okay? I go with the inductor, and what's going on inside the loop? Okay, inside the loop, think about it like this, and I go with my right hand. So the magnetic field is always inside in the same location. Every loop actually contributes. Let's draw it big so you can understand. So here it is. This is, here it is, right? So I want you to notice that the contribution of this current, which going from, let's do it like this, it's going like this, it's going like this, it's going up, going like this, going like this. Okay? And what is the magnetic field? The magnetic field is if I'm going in this direction, so it's going from that contribution, it's going inside here. And from that one, it's also going inside here. And for that one, it's always also going inside here. And it's a huge error, right? But all the circles do the same phenomena. Everyone is contributing to the magnetic field. And this is the reason we have a huge magnetic field inside and a really small one outside. I want to emphasize that the distance between the line actually tell us what is the size of the magnetic. Okay, so if the line are really dense, it means that the electric magnetic field is really big. Okay, so that's what happened inside the conductor. Okay, let's go back to the question. So the second reason is that there's more magnetic field that's actually poking my area. This is the idea, right? Okay, so there are more. Okay, so there are more strong magnetic, let's do B, magnetic fields that poking my area. They are more condensed. Okay, so this is just to give you a feeling. Okay, it's not a real question that's gonna appear in the exam, but I want you to have the feeling. Okay, the area is getting bigger, and also I become more sensitive to the magnetic because the magnetic is really dense in some location of the circuit. So that was the idea. So let's move on to the real question, and it's about the circuit that we drew before. Here it is. I need to do the little space here, resistor, and perfect L circuit. So the second question is actually to add what is the electric field in every part of any component of the circuit. Add the electric field. Okay, so let's do that. It's really easy. So first of all, inside the battery, okay, the current is going like this, right? Okay, inside the battery, I know this is the plus and this is the minus. So inside the battery, I expect to have a electric field that's going to the other direction. Okay, it's maybe confusing, but inside the battery, the thing of a battery is to take charge and put it in another voltage. So this is the chemical reaction that make that. And then I go to the resistors, and I know the current is going from here to here, so which means that positive charge moving in this direction. So I can say confidently that the electric field is going in this orientation. And if I look at the loops of the coil, So the inductor is actually ideal conductor. It's like this line, just turn around, right? Okay? It's not dissipating any energy, right? Like the resistor does, okay? So this thing, I can say confidently that the electric field is going in this direction, okay? So that's what's going on here. Perfect. And the second question, the third question is actually, what is the voltage that each one of the component produce, okay? Consume or produce, okay? Depending what we're talking about. So if I look at the battery gives us some voltage, I call it V0. So the battery giving us V0. The resistors, actually the voltage that is dissipating is, it's according to Ohm's law, VR is equal to I multiplied by R. And the inductor, what is the voltage that the inductor has? So inductor, actually the same concept, it's I and the resistance of the inductor. But we are talking about ideal inductors, okay? Which means they are ideal conductors. So this one is actually going to 0 and the voltage of inductor is actually 0. I say actually because we're gonna see in the next question something really special, and a lot of people confuse and think this is the voltage of the inductor. No, the voltage of the inductor is actually 0, okay? Ideal inductor. Perfect. But of course the inductor made of some conductive material which have some resistivity, but in this part of when we're drawing an ideal RL circuit, it does not have any resistance, and usually I think all the questions that I saw in this class were never about an inductor that have some resistivity. In the lab that you're gonna have maybe next semester, you're gonna see in the real life that you do have some resistance. Not everything is perfect. So the next question is to write the equation for Faraday using phi equal IL. Okay, phi B equal IL. So remember Faraday equation? What was it? It was that we have some voltage, right? Some voltage. If we have a changing magnetic field in time, okay? That's what we have. So let's write this one using that. So the minus state, this is Lenz's law. And if I put IL inside phi B, I can write DIL dt, right? And let's say that the inductance does not change. What I mean by saying inductance doesn't change, the geometry of the inductor does not change. Okay, nobody turn it around, add some loops, nothing happened. And nobody puts some material that does not change the material of the inductor itself, or put something inside the inductor, which means this is constant. If this is constant, I can take it outside and have minus di dt multiplied by L. It's outside of the derivative, and this is in the end equal to what? I can write it shortly, briefly, I dot, which means the derivative minus L. Okay, perfect. And what is a more mature way to write a voltage? A more mature way to write voltage is actually writing a loop. Here is the loop. It's a closed loop because it's a loop that produces the flux. The loop of E dot dl, right? And this is equal to the right hand side of the equation, which is minus I dot L. Perfect, okay? So this is a more mature way to write Faraday law, and I want you to notice that the loop here close some area. This area is A, and this area is the area related to phi B, okay? This is the where this voltage produced by this area, okay? So this is a Faraday law, another way to write Faraday law. And right now I want us to find a, we can clean that. And the next question I want us to find okay, I want us to find the current in the circuit that we have right now. What is the current in the circuit? So in order to find the current in the circuit, a lot of people expect me to use Kirchhoff's voltage law, which states that all the sum of voltage equal to 0, and I don't like this rule at all, okay? I'm gonna say why, okay? First of all, this idea is not true, okay? It's not holding when you have an inductor, okay? This law is incorrect when you have an inductor, so this is one reason. Second reason is that it's really complex to understand what are the signs. I put plus this voltage minus this voltage, it's not that clear. And the third thing is, this law is not basic. I always love to work with the basics ideas, for example, Maxwell equations, Faraday's law, Gauss's law, and from that to understand what are the limitations, what is the idea that I take and what's the idea that I cannot take. And this law, it's more obvious to, not that obvious to me, it's not that clear, so I recommend you to use Faraday law in this configuration for every cycle. Let's try to do it. So in order to do it, I need to declare a loop. So I declare that the loop, let's do it in the same direction of the current. I'm choosing my loop to be the area of this circuit. The loop is the conductor that go around. And if I do so, I need to sum all the voltages. E multiplied by dl is the voltage. So if I'm going in this loop, in this direction, this is my dl, right? I'm going on the circuit, this is the direction. This is my loop, dl. I encounter the battery, and the battery give me minus V0, right? This is this, I'm doing this. Minus V0. Why minus? Because I see that the electric field is actually against me. If I had a battery on the opposite side, so it was actually encourage me to go. So this is a minus V0. And then I continue, this is the DL, I continue to the resistor, and what I see, I in the direction of the electric field of the resistor. It's a small r, okay? EL, okay? So I actually adding IL to the equation. And then I'm going to the inductors, and what is the voltage of the inductors? I'm going with the inductor, but the voltage is anyhow 0. And this is equal to what? This is equal to, according to Faraday law, to the changing in the current minus the changing in the current, the derivative of the current, and multiply by L. What is L? The inductor, the inductors of the circuit. And I get this equation, okay? I can take this one to this side and have minus V0 plus IL plus IL equal 0. And I want to emphasize this mistake that people think that this is, sorry, I forgot the dot, that this is actually the voltage of the inductor. No, it's not the voltage of the inductor. The inductor have 0 voltage, but all the circuit, because it's a closed circuit, we have the area and we actually sensitive to the magnetic flux. And that's the reason we have this contribution, and I put it here, but it's not the voltage of the inductor, okay? It's really important. And it's a mistake that a lot of people do. Okay? So this is my ODE, okay? Let's organize this one. So, so if we're gonna write it in a more compact way, I can write I dot to normalize it at the beginning, plus R divided by L, multiplied by I, and this is equal to V0 divided by L, okay? And if I'm gonna solve this equation, if we're gonna solve it, what's the result that I'm gonna have? Okay, I'm gonna have this result. I'm gonna have I as a function of t, right? This is derivative of the time, function of time. This is a function of time, and it, and this one, maybe you need to check the units, but you're gonna find out that this one have actually units of time, actually 1 over time. This is 1 over second. And for that reason we are calling it tau, 1 over tau. Okay, tau sounds like t, right? Tau. So tau. And the solution for that equation, you can use Euler to solve it, but the result is actually V over R, and 1 minus exponent minus t over tau. Okay, and tau is just a short notation for this term, which is popping up here. You know what? Let's solve this equation. let's get to the solution. So you're gonna have the full answer. So how I'm solving this kind of equation? I said that the solution is probably exponents, because I see that if I'm gonna derivative it and sum it without the derivative, I get some constant, right? So the solution is to say that I have a homogeneous solution and a private solution. The homogeneous solution can be written as R plus R over L equals 0, which means I have that R equal to R minus R over L. So the solution, the homogeneous solution, is I equal to some constant multiply by exponent RT, and this one we just found out, it's minus R over LT, R over LT, I equal A exponent minus R over LT, and this is the homogeneous. And if I want to solve I'm coughing, it's not good in the corona time to cough, okay? So it's always embarrassing if you're coughing in a public place, right? Or sneezing or something normal, you know? Okay, so what is the private solution? So private solution, I always go as simple as I can. I need to guess some solution which is private, and then I'm going to sum them up, and this is the general solution. So the easiest thing I can do is declare that I is a constant. Okay, and what's gonna happen? It's gonna die here because it's a derivative. So if my IP is equal to I private, it's equal to some private solution, let's call it P for fun, private. So here it's gonna die out. So 0 plus R over L multiplied by P, the constant value, V0 over L. So I can find P, right? Can divide both. P is equal to V0 divided by R. So I found a private solution, right? P is equal to this. And now I need to sum them. And this is going to be the general solution. So let's sum them up. This. So the general solution to this RL circuit is I equal to A exponent minus RL T plus this one, V0 over R, right? And I want you, now I need some initial condition. If you're gonna have something to say about time, I can actually solve the equation because they don't know A, the constant. And what's really cool about inductors, that inductor does not like things to change fast, okay? You know the guy that wake up in the morning, I need to take his time until he's like full of energy. So inductors are just like that, okay? So inductors want to wake up slowly, okay? No matter what you do, if you want to change the condition, they need to adapt themselves really, really slow until it's happening. So before I actually put the battery on, let's say that I have here some knob, okay, here, and I put the circuit on. What was the current inside the inductor? Was 0. And at the beginning time 0, the current in the circuit was 0 because the conductor would not want any change to happen. He needs to wake up, he needs to clean his face, he needs to put some water on his face, brush his teeth, he needs to take the time slow till he's waking up. So I can confidently say that at time t equals 0, the current was also 0 because there was no current before. Okay? If I use this term, I can say that 0 equal to A multiplied by 1 because I put t equal to 0 plus V0 over R, and I find out that A is actually equal to minus V0 over R. And that's give me, put it here, take V0 outside of the equation and get this result. Okay? So next part of the question is to draw the result. So let's clean this up. So IT equal to V over R 1 minus exponent minus t over time. Okay? So let's draw this. So this is the time, this is the current. So at the beginning, what we said, the current must be 0, okay? The current must be 0, so we're starting for this point, do it in red, for this point. And what's gonna happen to this exponent with time? This exponent gonna die here. This have a minus, right? Here you can see the minus. So it's actually dying out. And I'm gonna stay with 1, multiplied by V over R. And what is V over R? Try to think about it. Look at the circuit that we have. V is the total voltage, right? V is the total voltage. R is the total resistance. It's like, what was the current if there was no inductor at all? So at infinite time, the current inside the circuit was like there is no inductor. So what happened? The involvement of the inductor was to take the time slow. If there was no inductor, it was boom. It was immediately current when I close close this. Of course, there was some, some in the real world there was some difference in time, but this is because there are always some inductance. Okay, even this circuit without the inductors is like a huge loop, right? So that's the idea. There are always some inductors, but in ideal circuit, of course, it's immediately the maximum value. Okay, and I want to talk a little bit about this tau. See this tau? It's really special. Why it's really special? Because tau is actually give us some feeling about the time, about where we are located in the phenomena. So if we're gonna put here 5 tau, okay, t equal to 5 tau, I'm gonna get the result. This term gonna be something like 0.9996, okay, which means 5 tau is kind of like saying you are in infinity, okay? A lot of time when doing in control system or in aerospace engineering, when somebody said 5 tau, it means really do the end of the phenomena. It's in the end of the phenomena, okay? But if I put t equal t equal tau, something really special happening, okay? So here it is. This is approximately tau. Tau, what's tau give us? If you're going to calculate this, you're going to find that this is equal to 0.67, okay? It's like it's like more than half of the phenomena is behind us. Okay, that's the idea of tau. And I want to emphasize the tau is just that. It's L over R. See, it's 1 over tau. It's L over R, okay? So the phenomena of the resistance and the phenomena of the inductance actually determine the time that's going to take us to reach the final current, okay? The end of the phenomena. So this is the idea of really simple, basic RL. And now we're going to dive into a more complex RL configuration, but it's going to be part of the same, okay? So let's move to the next question.